this is Drew. Welcome to watch the video. I'm going to talk about my research root choice analysis on sharing microcars. It was conducted in Nagano University, Japan. It was also cooperation with Toyota Motor Company. My talk connects several parts of what I learned and what I did in this whole research process, from my introduction background to how I operated and analyzed the data, to the methodologies I utilized, and to a results discussion part and a brief conclusion. So if you are interested in any part, any detail of this research, you can find my contact at the end of this video. I'll start from the introduction of this project with its background, objectives, and important literatures. My research was dealing with the sharing microcar called Hamo, which is a transportation service operated in Toyota City, Japan. When you want to travel, you borrow one of Hamo car at one of these charging stations, you drive, and then you return it to another station near your destination. The topic of this research is root choice behavior, so I decided to construct a root choice modeling framework to investigate, firstly, what kind of roles or route characters has important impact on Hamo drivers' route choice. And secondly, since Hamo is a transporting service rather than the conventional private cars, so I thought it would be interesting to find out the possible differences between the new users and experienced users of this mobility service. I studied scholars' previous works under the big topic of root choice modeling, checked different choice generation algorithms, different root choice models, and also some important index as well. I decided to design my research structure by applying the major methodology of sampling of alternatives and random walk generation. I also decided to conduct experiments on structural parameters. In the common data analysis part, I'm introducing how I dealt with the Toyota City GIS files and the Hamo operation data, and there's also a data description under that. The whole very big road network was cut into a proper scope, like shown in the picture, and according to Google Maps, according to the exact Hamo station's coordinates, I added links linking these stations and the existing links. And then I unify all the attributes and formats of all these links to finally obtain a directed graph to be imported into Python for further use. Toyota Motor Company provided a Hamo operation data of a couple of years. I chose to use 1 month data to obtain the sample set for further model estimation. After data cleaning and selecting the feasible trips for doing models, I obtained a sample set of 769 trips, and I chose to use 6 months before that 1 month data to analyze the using history and frequency. By calculating the using frequency and history of all the users, the whole sample set was divided into 4 groups. The novice group represented the users who had the shortest history and the lowest frequency of using Hamo, and the experienced group had the longest using history and the highest frequency of using this mobility service. The further comparison and analysis would be conducted between these 2 groups. The first figure shows the distance time cost distribution between this novice group and experienced group. It is as expected that new users they travel long distance and spend more time, more money on this service. This one shows 2 groups distributions on their routes, intersection numbers, right turn numbers, and the road width weighted by length. Some obvious difference could be found from the figures, but how these factors affected these drivers' route choice behavior should be explained and discussed in further steps after modeling estimation is done. By calculating the Y-link percentage of each group's chosen routes, no big difference was found, but I noticed another phenomenon. There have been big overlap among all the route alternatives for each OD pair. This is very suitable for using one of the famous and classical root choice model, the path size logit model, or the PSL. Methodology connects several sections of different technologies. Some of them are paradigms for root choice modeling or discrete choice modeling research, and some of them can be modified or transferred to other research objectives. So this is the biggest part of this video. Because exhaustion of all the possible rules connecting each OD pair in a very large road network is neither feasible nor necessary. So it is believed that it's better to use a subset and the conditional probability to calculate the choice probability of one option. And the conditional probability, like showing the red box, has been derived into values like showing the blue box. So the problem has been transferred into calculating actually 4 values: the utility function of one option times and the probability of path being generated from universal set and the path size for one alternative. To realize the idea of sampling of alternatives, the random walk generation was firstly conducted to generate Rn paths, and the actual chosen route was identified and added to the Rn paths to form a subset with Rn plus 1 alternatives for further modeling use. Then the alternatives variables, all the attributes, values were calculated, and the model specification procedure was done. In this research, I experimented on the performance of different combinations of random walk shape parameters, combinations of different variables, and also check the impact of using different numbers of generated routes. Instead of using traditional methods such as k-shortest path or labeling approach, the random walk generation technology generates routes by giving each link a weight based on its distance, the shortest path, and simulating the process of one vehicle travels randomly from its origin to destination. The randomness level of this process is controlled by the value of B1, like shown in the red box, and it had been developed to be a structured shape parameter form, like shown in the blue box, which has a very big advantage in generating realistic paths or avoid generating path with too many duplicates. I firstly examined the effect of unstructured shape parameters, the fixed B1 value. When using a smaller B1 value, it generates very diverse paths, which was good. But for the longer distance OD pair, it just generated very long distance routes, which was not so realistic. On the other side, when using a bigger B1 value, the path kind generated was less diverse. But for any OD pair distance, the route length generated was realistic, similar or a little longer than the shortest distance. So there is a trade-off between using a smaller B1 value or a bigger B1 value. Then I tried different structure shape parameters and tried to find an ideal combination of B3 and B4 value. When using 50 and 15, diverse paths were generated, and the path length were very well controlled to be 1 to 1.5 times the shortest path distance. I also calculated and examined the index of overlap and coverage. As the number of routes generated gets higher or a more diverse paths was generated, the coverage index was clearly raised in this random walk generation process. Next step is route identification. In this part, I developed a map matching algorithm in Python dealing with GIS files, listed several steps of my algorithm, and its performance was shown picture on the right. After recognizing the actual chosen routes and adding it to the former Rn paths generated by random walk generation, a final choice set was formed for the further steps of modeling. I considered using 7 variables for the original utility function: distance, time, money cost, intersection number, right turn numbers, road width, and white link percentage. But to actually include how many of these variables or what kind of combinations of these variables to form the final utility function remains a problem for model specification part. I first examine the correlation between every variable with every other variable. Both the figure and the correlation matrix show that the variable of distance and time, they have very strong correlation with other variables. Also, the check of multicollinearity, the very big VIF value of distance and time, these two variables, they confirm this problem. So I was thinking to exclude at least one of distance or time variables. Then I run examinations on the multicollinearity of different combinations of 6 variables and 5 variables. As you can see in the red boxes and the blue boxes, 6 variables combinations didn't present as good performance as what the 5 variables combinations did. So I decided to use either of these two 5 variables combinations to form my final utility function. I finally had the results after a lot of running of modeling programs. In this part, I will discuss both the modeling estimation and some empirical findings. The first comparison was between structured and unstructured shape parameters using exactly the same variables combination. We can see from the adjusted rho squared value, the structured random walk shape parameters had provided clearly better performance and model estimation results than the unstructured parameters. The second comparison was due to my assumption that generating different numbers of alternative routes would have impact on model estimation results. But as shown in the picture, generating 10, 20, or 30 routes, they have very similar estimation performance. This one shows how I chose variable combinations to confirm my final utility function form after a modeling estimation procedure. I basically consider 3 aspects: the signs of the coefficients estimated, t-stats value, and the correlation and multicollinearity among the variables with each other. As you can see, one of the coefficients of cost is not significant, so it was excluded. For the 6 variables combination, as I mentioned, I already decided to exclude at least one of distance variable and the time variable. So finally, these 5 variable combination, like shown in the blue box, was chosen. For the novice user group, the 6 variable combination without time variable had already showed very good performance of model estimation, so it was chosen to be the exact form of utility function. Experienced user group had a similar situation with the whole sample set, as the distance and time variable could not be both included. So the 5 variable combination, like shown in the blue box, was finally chosen. Empirical findings were the answers to the 2 questions raised at the very first beginning of this research. The process was generally done by checking the signs and values of every coefficient. The distance, intersection number, right turn numbers coefficients were negative, which were actually consistent to our common sense. Especially turning right were believed to be not as so convenient as turning left in Japan because vehicles drive on the left side of the road, and people try to avoid turning right. The signs of coefficients of road width is positive. It had some possible explanations. For example, because Hummer is a very compact, small vehicle, people tend to drive on bigger roads to obtain better security sense psychologically, and it was easier to refer to help when malfunctions of the service happened or even accidents happened on the road. Signs white link percentage was negative It was kind of tricky, but still interesting. Checking the modeling results of novice user group and experienced user group, the comparison between these two groups didn't show large difference of their rituals behavior when using Haml, while some gentle differences did exist. For example, the novice user group they tried to avoid routes with longer distance or routes with more intersection numbers. On the other side, the experienced user group they tried to avoid the routes with more right turn numbers, and they tried to drive on routes with larger road widths. Okay, now some points of conclusions to wrap up this research and my talk. My work studied sharing microcars retroactive behavior with a framework of a path-side logit model, sampling of alternatives method, conducted experiments on random walk generation, and so on. Verified that structured random walk parameters provided better estimation results, and the path generation numbers had really little impact on model estimations. It studied microcars retroactive behavior and confirmed that drivers resisted on longer distances, more intersection numbers, more right turn numbers. It also found that Haml users have a positive tendency to routes with larger road width. It gained some insights of choice differences between novice user groups and experienced user groups, like I mentioned in the last section. The limitation of my work lied in that if data with more abundant road or route information could be used, or even personal information could be involved, I believe it would provide better modeling results. For the future of this research, I'm thinking to construct a model that can particularly deal with MAAS users using frequency and using history, because I believe the mobility as service is a very big trend of future transportation. Okay, thanks for listening and watching. If you are interested in the direction of root choice analysis, or if you want to discuss any specific part of this research, just leave a comment or contact me. Okay, take care. See you guys.